Hello everyone, welcome back to Deterministic Optimization. Let's continue our discussion on SOCP, SDP examples. So in this lesson, we're going to learn about a new class of problem called extremal ellipsoid problem or extreme ellipsoid problem. And we're going to discover a formulation that involves both SDP constraint and SOCP constraint. So remember in the previous two lessons, we looked at a linear classification problem which can be formulated as SOCP. And then we looked at an experiment design problem that can be formulated as a SDP. And this lesson, we're going to learn a more complicated problem which needs both SOCP and SDP constraint. Okay, so what is extremal ellipsoid problem? Suppose we have a set of data points. D is a set of points V1 to Vm. So you think about these are measurements or some data that you collected. And what you want to do is you want to find a smallest ellipsoid that contains this set of data points. So suppose these are the data points that you collected, and you want to find a ellipsoid that contains it. There are, of course, many ellipsoids that can contain this set of points, but you want to find the smallest one that still contains this. Why do you want to do this? You can think about this ellipsoid as an approximation to the set of data points, right? It exactly contains all the data points and is the smallest one. So the shape of this ellipsoid reflects the aggregate shape of these data points. And the ellipsoid can be modeled in a very compact way. So instead of using a lot of points here, we can represent all these points by a very simple object, an ellipsoid. So this is one of the motivations behind why do I want to do this. There are other motivations. This finding a smallest ellipsoid that contains or circumscribes a bunch of points is a fundamental problem in computational geometry. Okay, so let's see how to describe an ellipsoid. Well, an ellipsoid is described by only two things. One is the center, where the ellipsoid is centered. The other is what its shape. So the center is a vector C. Remember, these are high-dimensional ellipsoid, an n-dimensional ellipsoid. So C is an n-dimensional vector. And then we need a matrix to describe the shape of this matrix. So that matrix called, of this ellipsoid, that matrix is called Q. So Q is an n by n matrix. And furthermore, this Q has to be positive semi-definite or positive definite. And given this two, the ellipsoid is described as the set of points x such that x minus c transpose q times x minus c less than or equal to 1. Okay, so this is a ellipsoid. And the shape of the ellipsoid is described by q. By shape, I mean how round it is, how big it is, and how long it is along one axis, how long it is along any axis. So the shape already, shape matrix already contains all the information about the orientation of the ellipsoid, how round it is, how big it is. So everything is here. And C is where do you shift it so that it's centered at C. All right, so how do we measure the size of an ellipsoid? As we said, we want to find the smallest ellipsoid that circumscribes a set of points. So one common way to measure the size of an ellipsoid is to use volume, right? How big the ellipsoid is. What is the volume of the ellipsoid? How do I measure a volume? Well, it turns out the volume of an ellipsoid is proportional to the determinant of the inverse of the shape matrix Q. Okay, so in other words, the shape matrix, if the determinant is big, then the ellipsoid is big, has a larger volume. And this is proportional, so it's independent of C and Q otherwise. It depends on the dimension, but the dimension is fixed. So it's really the volume of E really depends proportionally to the determinant of Q inverse. Okay, see, we have an inverse again. But don't worry, we're going to figure out a way to deal with that. So we want to minimize the volume. However, this determinant of Q inverse is not a very nice function to deal with because we have determinant. Determinant is not a convex function or concave function. But it turns out that instead of minimizing directly the volume, we can minimize the log of the volume because log is an increasing, monotone increasing function. So minimizing x is the same as minimizing log x, right? So I'm going to look at the function of log determinant of Q inverse as a function of Q. So fq is log determinant of Q inverse. And this function magically turns out to be a convex function of Q. I'm not going to prove this, but you can take this as a fact. And this is a very important fact that the log determinant function of a matrix inverse is convex. And if you know a little bit of matrix analysis, determinant of a matrix to the power, to any power, is the determinant of the matrix itself and then the power to the determinant. So in other words, determinant of Q inverse is equal to determinant of Q, the whole thing, to the power -1. So, and then we take log, that means is the negative of the log determinant of Q. So log determinant of Q inverse is equal to the negative of log determinant of Q. So if log determinant Q inverse is convex, that means log determinant of Q is concave. All right, so now we can minimize the volume of a circumscribing ellipsoid or a containing ellipsoid by minimizing its log determinant Q inverse subject to this. Every data point has to be contained in the ellipsoid. In other words, that means every data point has to be inside the ellipsoid. That means every data point has to satisfy this constraint. That is the constraint for a point being in an ellipsoid. So that constraint exactly Vi minus C transpose times Q times Vi minus C less than or equal to 1 for all I, for all data points. And the variable in this optimization problem is Q and C. And we also need Q to be positive semi-definite. This actually is not a convex optimization problem. Although this is convex, the objective function is already convex, but the constraint is not. See, the constraint has a variable here, and variable here, and variable here, and they're multiplied. So this is a multiply of a cubic constraint. It's not convex. So we need to do some transformation to make it convex. All right, so how to do that? Here is the trick. Because Q is positive semi-definite, right? Q is a symmetric positive semi-definite matrix. For every symmetric positive semi-definite matrix, there exists another matrix A such that Q is equal to A times A. Okay? A is symmetric, so A times A is A squared. So Q should be equal to A squared. That is a fact true for any positive semi-definite matrix, can be written as another matrix squared. So in other words, A is Q square root of that, square root of Q. So then I can look at what is the determinant of Q inverse in terms of that, in terms of A. So determinant of Q inverse is determinant of A inverse squared, right? Because A is Q to the power 1/2, or Q is A squared. So Q is A squared, Q inverse is A inverse squared. So determinant of Q inverse is determinant of A inverse squared, but determinant of A inverse squared is the same as determinant of A inverse, the whole thing squared. This is a property of determinant. So then if I take log of determinant of Q inverse is equal to log of determinant of A inverse whole thing squared. But by taking log, I can pull this squared out of log. So then it's twice times log determinant of A inverse. So you see that log determinant of Q inverse becomes proportional to log determinant of A inverse. 2 does not matter. It's not significant because minimizing a function is equal to minimizing a constant times that function. 2 is a constant. So then we really only need to care about log determinant of A inverse, and this is convex in A, as we already see. So we keep the convexity of the objective function. What about the constraint? The original constraint here is non-convex. But because I have written Q as A times A, then I'm going to have Vi minus C transpose A times Vi minus C. Because A is symmetric, so this whole thing replace Q with AA is the same as A times Vi minus C whole thing Euclidean norm of that, right? Because the Euclidean norm of this is exactly this whole thing transpose times this, which exactly is equal to this original constraint. So if you look at this, well, this is a convex constraint in A. A is a variable, but C is also a variable. So how do we do that? Well, A times C is a variable, right? A times A is a variable, C is a variable, A times C is a variable. So I'm just going to make that variable, call that variable B. So then I have A times Vi minus B, Euclidean norm, less than or equal to 1. This is a second order cone constraint in A and B. So if I can find A and I can find B, then I can recover what C is. C is just A inverse B. So this is my reformulation. Oh, what I got is this. I have minimize log determinants of A inverse. We know that this is a convex function in A. And I have this constraints, A Vi minus B, norm of that, Euclidean norm, less than or equal to 1 for all data points. And A should be positive semi-definite. So this is SDP constraint. This bunch of SOCP constraints. Remember this constraint here. You can write this constraint as AVI minus B as a column vector, and then attach another one to it. This is the n+1 dimensional vector. This vector is in n+1 dimensional second order cone, right? That's exactly is the reformulation of this. And A is, the matrix A itself should be positive semi-definite. So everything is nice. This constraint, SOCP constraint, this SDP constraint, this is convex objective function. So this is a convex reformulation of the minimum volume circumscribing ellipsoid problem. All right, so let's summarize. We have learned what is the minimum volume circumscribing ellipsoid problem. And we have formulated a convex SOCP SDP model for it. That's it for this lesson. Thank you.